Dear colleagues, dear friends, it's time to start our morning plenary session. Let me introduce myself. I'm Alexander Trifonov from Institute of Organoelement Compounds, Moscow. It's my great pleasure and honor to chair this morning session, and we start with the first lecture, and it's my pleasure to announce the lecture of Professor Herbert Gleiter. Professor Gleiter was one of the first who in the 80s formulated the concept of new materials, so-called nanomaterials. Now he's appointed at the Technological Institute of Karlsruhe, and also he's the head of Institute of Nanoscience at Nanking University. He is a member of 7 national academies of sciences, and he was awarded by a great number of awards and prizes. Among them is the Leibniz Prize, Helmholtz Medal, Catenius Medal, which is the highest award of German National Academy of Sciences. And he's a member of American Academy of Science and Art, National Academy of Science of the United States, member of European Academy, National Academy of Science of India, etc. Professor Gleiter, please, the stage is yours.
Well, good morning, everybody, and thanks, of course, for the invitation to that conference, as well as for the kind introduction. As you can see, the topic of my talk is non-crystalline nanostructured solids, so-called nanoglasses. And what I want to do is to show you, or try to present evidence, that these nanoglasses represent a new kind of solid-state structures, which seems to open the way to new, not only solids, but new properties, and therefore new technological applications. And in order to do that, I will divide my talk in 2 sections. I'll first say briefly about a few words about the present background in terms of technology of materials, and then go on to the nanoglasses, show you what it is and why they are new and what is so specific about them and why it is so promising. So let me start with today's technology. And as you all know, in today's technology, there's a very strong preference for crystalline materials. This applies to metals, to semiconductors, and to ceramics. And the reason for that is very simple. We can change the properties of crystalline materials by introducing crystal defects or chemical defects, and in this way produce materials that are suitable for technological applications. And I'll show you 2 of these examples, crystal defects here. This is a high-resolution micrograph of palladium polycrystal, 3 crystals, and here grain boundaries. And you can see in these boundaries the atoms are arranged in different ways than in the crystals. And these different arrangements, by means this defect, that causes dramatic property changes. For example, the diffusivity of this palladium goes up by about 20 orders of magnitude at ambient temperatures. 20 orders of magnitude, that's about the growth rate of a tree to the speed of a car. So it's a very dramatic change. And here is a chemical defect, silver and iron. And in these interfaces, silver and iron atoms are nearest neighbors, and that also changes the properties. For example, the strength of such a material is 4 or 5 orders of magnitude higher than pure iron or pure silver. Now, such defects, chemical defects and crystalline defects, cannot be introduced in today's glasses. In today's glasses, we normally produce them by quenching the melt or the vapor, and then we get a structure which is shown for a 2-dimensional case, silicon dioxide here, which is a random arrangement of silicon and oxygen, but no such things like such chemical defects or structural defects. And therefore, we cannot manipulate the properties of glasses in the same way as we can do it for crystals. And that is the main reason why glasses are far less often applied in technology in comparison to crystalline materials. On the other hand, what that teaches us is if we succeed in producing glasses where we can introduce structural defects or chemical defects, we would open the same door as we have it today for these crystalline materials. And this is what leads us then to nanoglasses, this idea, and I'll show you that, how we do it. It's in principle a very simple approach. What we do is we take a piece of melt, but we not quench or cool the melt rapidly as it is done in the last 8,000 years, but we break the melt up in very tiny droplets with the size of a few nanometers. And we cool these droplets rapidly so they form clusters of a glass with a diameter of a few nanometers, 1, 2, 3, 4 nanometers. So we have very tiny glassy clusters, and these glassy clusters we take and consolidate them at high pressure, several gigapascals, into a solid. So these are the clusters, and these are the interfaces between these clusters, and this solid is called a nanoglass. A nanoglass because it's glassy regions here and a nanometer size. So it's like a nanocrystalline material, but not crystals, but glassy regions. And it's now the glass interfaces, or the atoms in these glass interfaces, that produce the new effects. What we see, and I will discuss that in a minute, in these interfaces we get new atomic structures, we get new electronic structures, and therefore new properties, got very dramatically different properties. And this is the reason why nanoglasses become very attractive materials. Let me show you a few things what we know today about these nanoglasses. This is an atomic force micrograph of the surface of a nanoglass when you fracture it. And this is a transmission micrograph of a gold-silver nanoglass. And what you can see are the brighter areas here. These are the glassy regions. And then the dark lines in between, these are these glass interfaces. So what you see here is essentially this here. The interfaces are here, and the brighter region is that. So this is the structure which we see, which is, of course, not surprising. The big surprise came when we measured the density of these interfaces. When we measured the density of these interfaces, we found that their density is reduced in comparison to the glass, typically by about 15, sometimes more %, and the number of nearest neighbors in these interfaces dramatically reduced by about 20%. You have to keep in mind this is very dramatic because when you go, for example, from ice to water, you change the density less than 2%. And now here we change the density from the glass to the interface by 15 or more %. So it's a very highly diluted state of matter. It's about 1/4 to the critical point. So it's a new density, a new structure of these things. And one can directly see this change by looking at a two-dimensional system, two-dimensional silicon dioxide. Here is a glassy region, and here you see such an interface, and you can see that it's less dense, and the number of nearest neighbors is reduced. But not only that, we get new atomic structures in these interfaces, we also get new electronic structures. And this is what we can see here. This is a nanoglass made out of iron 90, scandium-10. And this is the Mössbauer spectrum of the iron 90 scandium-10, the glassy region. It's a single-line spectrum. This is the same spectrum what you see when you take a bulk piece of iron 90 scandium-10. The new and surprising effect came when we looked at the interfaces. When we look at the interfaces, the Mössbauer spectrum all of a sudden is very different and has 6 lines. And 6 lines indicate the interfaces are ferromagnetic. So we have a material which is as a glass and as a crystal, a paramagnetic material. When we transform it in a nanoglass, it becomes in the interfaces a ferromagnet. But not only that, but we also see that one spectrum for all the interfaces. So all the interfaces in a nanoglass have exactly the same structure. And there was another big surprise is when we take the nanoglass, deform it or irradiate it and destroy the interface, it comes back exactly in the same way. So this is an equilibrium state of matter. No matter what we do, all interfaces end up with that kind of structure. which is a ferromagnetic state. And then, of course, we looked a little bit more into this thing and try to find out why this is a ferromagnetic state. And what turns out, I'll just show you his one result. In these interfaces, what we see is, this is for iron 90, scandium 10, we see a very high density of BCC clusters. You can probably see them as bright spots here. So the interfaces are not uniform, but they consist of BCC clusters. BCC is a structure when you crystallize the material, and this is a cluster with the size of one elementary cell. And these elementary cells are separated by isolated atoms from each other. So what we have is a structure which is a kind of strange compromise. On the one hand, we have the fingerprint of the crystal with these in the elementary cells, and they are separated by individual atoms statistically arranged through a gas-type structure. So it's a compromise between a gas and a crystal, and that is the structure which we see. And if one does we started now ab initio calculations, one can start to understand why we form a ferromagnetic state in that highly diluted state of matter with this new structure. And that seems to be the equilibrium state of disordered matter. So glass is a quenched-in liquid, and this is when you supply the liquid with free volume, ask it to rearrange to the lowest energy state, and this is what comes out here. Now, of course, with this new structure, one would expect new properties, and this is indeed so. I'll show you a few examples. This is, for example, the magnetization of a scandium 75 iron 25 nanoglass. This is the melt-spun ribbon, and magnetization as a function of temperature, and you can see it's way down there. Now, if we take the same material and produce it in the form of a nanoglass, then the magnetization goes out by a factor 10. It's a red curve up here, and it becomes a strongly magnetic material. In fact, if you would go back to the iron 90 scandium 10, we can go from a paramagnetic to a ferromagnetic state. Here we just increase the magnetization. A second effect, which I want to show here, is the surprising effect of the biocompatibility. This was a titanium zirconium glass in form of a nanoglass, in the form of a melt-spun ribbon. And when we put cells, osteoblast cells, these are model cells, on the surface of the nanoglass, they grow by a factor 100 times faster than on the surface of the same, chemically same material, but as a melt-spun ribbon. This is shown here. This is a melt-spun ribbon of this titanium nanoglass, and this is the surface of the melt-spun ribbon, and this is the surface of the nanoglass, and the green spots are the osteoblast cells. And what we see is as soon as the osteoblasts are there, they rapidly multiply and cover the entire surface. So the obvious, of course, application of this is to coat implants, bone implants, tooth implants with such a nanoglass, and when you put this implant then in the body, it grows in by a factor 100 times faster than a classical implant. Now, we have done a few experiments already. For example, a tooth of a dog, when you take it out and you put an implant, a tooth in, it takes about a week to grow in. If you do it with this one, it's less than an hour and the tooth is grown in. And now people trying this one here with implants of bones, hip implants, for example, for monkeys, and instead of about 2 months, it goes down to a day or two for the implant to go in. And that's a big progress, because then they don't need a second operation. You can put, the implant is coated with a nanoglass at the surface, put in, and then after a very short time it's grown in. So with one operation, you can take the bone out, implant the thing, close it, and it's growing in a short time. And then third thing, what I wanted to show here is the mechanical properties. It's again the same nanoglass here, scandium 75 iron 25. And when you have it as a melt-spun ribbon, it behaves normally. It deforms elastically. There's stress versus strain. It deforms elastically, and then it brittle fractures. Well, this is what, of course, we all know, that such melt-spun ribbon are brittle. But now if you make it in form of a nanoglass, it becomes a ductile material, And when you look at a deformed specimen, it looked like a piece of gold or copper. So again, the mechanical properties are very different. There are many more of these properties. And what comes out in all the cases we had so far, when we look at a property, we get surprisingly new effect, and many of them are very attractive. And that, of course, is obvious for technological applications. Now, so far, in all the cases I've shown you, I've considered nanoglasses that consist of where all the clusters, going back, where all these clusters here have the same chemical composition. Now, there is no need for that. We can, of course, also use clusters with different chemical compositions. And then we end up with nanoglass alloys. And this is what we did here, and I'll show you one example where we see also very spectacular effects. The nanoglass I'm considering here is a nanoglass consisting of ionic nanoglass, amorphous silicon oxide, and the metallic clusters are a palladium silicon iron glass. So this is a metallic glass, this is an ionic glass, and when we put them together, the surface looks like this. This is not surprising. You see the big blobs, they are the metallic parts, and the smaller ones are the ionic parts. And when we scan across it for the composition, then what comes out is also not surprising. We get very big fluctuations. There's a palladium concentration as a function of position. We have some areas where we have a very high palladium, then zero, high. This is each time we hit a metallic glass particle, we get a high concentration. When we hit a silicon oxide, we get low. The big surprise came when we annealed this material for only about 3 hours at a moderate temperature of 250. What we saw is that all these clusters disappeared, and we got a very uniform structure, and the composition became very uniform. In other words, all these clusters here disappear, and they form an amorphous solid solution of an ionic material in a metal. This is something you could never do in the crystalline case. If you have, say, silicon dioxide and iron, you can do whatever you want. It will never form a solid solution. Now, in this case, it does form solid solutions, and we tried some other systems, always the same answer. We can mix and alloy components which are immiscible in the crystalline state. So this is a very fundamental progress. When you look in earlier days, Bronze Age, Iron Age, Semiconductor Age, it's always that you take one component, tin and copper, and you get bronze. Or iron and nickel, you get a steel. But now we can alloy components like silicon dioxide or silicon oxide in a metal. So you can alloy a window glass with a piece of iron in this state. If you look back now, of course, that's not quite surprising. You think about it. When you have sugar and ice, you cannot mix it. When you have honey and water, you can mix it. So this is exactly what we see here. In the amorphous state, we can mix components that are immiscible in the crystalline state. And that opens up a whole new world of alloys where we can then mix ionic with metallic materials. In other words, if we change the chemical composition, we can tune the bonding of the material from an ionic material all the way over to a metal. And depending on what composition you choose, it's more metal or more ionic. And the metal is no longer a normal metal, because then you have sitting the ions of the ionic materials in the metal. That means the conduction electrons have to screen these ions. They are either repelled or attracted, so we get very large fluctuations in the electron density. This is a very new material, it should have new properties, electronic, optical properties, and so on. All we have so far, what we know is that we can do it, we know how to do it, and that we form a family of alloys which did not exist in history so far. Now, so far, all the things I've considered here are, of course, electrically neutral materials. We have these clusters, and they are electrically neutral, bring them together, and we are now. What I want to do is go one step further and go to nanoglasses, which are electrically not neutral anymore. In order to do that, we did the following. We take a two-phase nanomaterial, here black and white, this black and white, and then we etch out the one component, say the black one here. An example of that sort is a gold nanoglass, and we etched out the other part, and then you get nanometer size holes inside of the gold. And the structure looks like this. This is the gold, and this is the material which is etched out. And now we fill in an aqueous electrolyte into this into these voids, and then we can apply a voltage between the electrolyte and the metal, the gold, for example. And if you do that, then of course we get electric charges at these interfaces, and as 50% of the atoms are sitting in these interfaces due to the nanometer scale structure, then of course 50% of the atoms can be changed in their electronic charge. So we can tune the charge of the atoms in the way we can do it, and by applying the voltage. And that of course changes the properties. We tried that for a few systems. I'll show you 3 examples. The one is the charge-induced superconductivity of strontium titanate. Strontium titanate in the pure form is an insulator. And what we did, we have a strontium titanate, thin film, electrolyte, KClO4, and here a platinum gate, and we apply a voltage. And what we can see is when we apply a voltage and charge the strontium titanate highly, then the surface of the strontium titanate becomes a superconductor. And you can see here when we apply a voltage of about 0.4, we get the superconductivity at 0.4 Kelvin, so we can transform it from a normal conductor in a superconductor and back. And the same we can do with porous strontium titanate, where most of these atoms are sitting in the interfaces, so the entire strontium titanate can be switched between a superconductor and a normal conductor. Another application is artificial muscles. By using the charge density-induced variation in length of carbon nanotubes, we can build artificial muscles. What we do is we have the muscles, and they are sitting in an electrolyte, and when we apply a charge, then these carbon nanotube threads twist, and when we decharge them, they untwist. So you can see here the twisted state, and the untwisted state. And by twisting and untwisting, the length of the carbon nanotube changes. And so when you put that into the body, at a position where somebody has lost its muscle, you can, by applying a voltage, shorten and lengthen this structure, and that acts then like a muscle. If it is short, then the arm will be stretched. If it is long, the arm will be bent. There's, of course, a spring on the other side. So these materials can be, or the charge-induced length variation can be used for building artificial muscles. The third example I wanted to show of property changes, which is also very dramatic, is the magnetic moment of palladium-nickel nanoglass. By applying an external voltage of about -0.4 to +0.4, you can change the magnetic moment of the nickel by about 45%. So you can again switch the material forth and back by having this locally very highly charged state. So that is a new aspect of the nanoglass, that we can now change properties by applying external parameters like a voltage and change then the properties. A last factor also which opened up with the nanoglass are materials where we can have switchable atomic structures. I'll show you that, and they will lead to single atom transistors. What we did is the following experiment. We have here 2 polymer-coated gold electrodes here, and they are coated by a polymer, and they form a gap here of about 50 nanometers. And they sit in an electrolyte which contains silver atoms, and when we apply a voltage between this gate here and these electrodes, then silver atoms are deposited in the gap between the electrodes. That is not surprising, but what was a big surprise was when you look at these silver atoms, they start to self-organize and form an ordered structure in that gap. And the more atoms you deposit, the higher become the conductivity, and the conductivity increases by steps of 2e²/h. E is the electronic charge, h is Planck's constant. And so you can change the conductivity by steps up and down discontinuously. The smallest step is shown here, we change the gate voltage between 0 and 25 millivolts. So this is the voltage between here and here. And what you can see is that then the conductance of these two electrodes jumps up from 0 to 1 e squared over h down to 0 again, so very reversibly. What that means in physical terms is what we have here the two electrodes, and when we apply the 25 millivolts, we form a one atom conducting channel which just produces 2 e squared over h. When we then reduce the voltage to 0, then the channel opens up, conductivity goes back to 0. When we close it again, it comes up and down. So what that is it's a single atom transistor, but the attractive thing is it forms spontaneously. You don't have to manipulate anything. You just apply the voltage, and the atoms jump in these places, forth and back all the time. And a very important aspect of that transistor is that the energy consumption of that transistor is only about 10 to the minus 4 of the energy consumption of a field effect transistor. And that is important in the future because at the moment we already consume a few percent of our energy for electronic devices. Now if we have the next generation, normally in 15 years, the energy consumption goes up by a factor of about 10%. That means in about 10 to 15 years from now, we will use half of our energy for electronic devices unless we succeed in building transistors which are far less energy consuming than what we have, and that might be a candidate for such things. Now a new aspect was this manipulation of the atomic structure, and so let me finally close by looking at the situation as a whole from the historical point of view. When you look for it at a historical point of view, then what you can say is that the technological application of crystalline materials today and in the past, that has opened us the path for today's technologies. This is based, as I indicated at the beginning, on the use of crystalline materials, metal, semiconductors, and ceramic materials. So in that sense, we are living at the moment primarily in a crystal age. The bronze, iron, metal, semiconductors, they're all crystalline, they have new properties and they allow us new technologies. So our present age is characterized by the use of crystalline materials, so in that sense it's a crystal age. Now these nanoglasses, they open the new option. The technological application then may open the door to a new age of technologies, the technologies based on the new properties of these nanoglasses. So that would be then a glass age, because that technology age would then be based on non-crystalline materials which we couldn't use today because we are not able to manipulate the properties of glasses in the same way as crystals. And that barrier would be removed now by these nanoglasses instead of the melt-spun ribbon. And that could be a new thing. But now comes the catch. At the moment, we cannot produce these nanoglasses in large quantities. We can produce them a tenth of a gram, at the most a gram. But for, of course, technological use, you need tons or kilos. But if somebody would find a way to produce nanoglasses in such large quantities economically, then there should be no more barrier to use or develop a technology based on the new properties of these nanoglasses. So we are in a state of, that has often happened in the literature when you, for example, consider the semiconductors. During Shocklay's time, people laughed about it and said you will never get a material which has an impurity level of 10 to the minus 16, and therefore you cannot build a doping. Then came the zone refining and the problem was solved, and we have today's technology. So if something would come like the zone refining here, somebody producing these materials in large quantities, then there should be no more barrier to develop a glass age. Let me finally show you the people that were involved in all of these studies, and you can see they come from all over the place. They come from Japan, from China, from India, Russia, Europe, United States. The reason is when we do this kind of research, normally when we have a kind of measurement or study, we approach a group which is well known, has all the expertise. So by bringing our knowledge together, we get a very short-term and a competent solution. And that's the reason why we have this very large group of people. And the institutes where these things were carried out was when I started, was in Saarbrücken, and then now at the moment, one part of the work is carried out at Karlsruhe, and these are two new institutes in China. This is the one which is already standing in Nanjing, and a very new institute is presently being set up by the Chinese Academy of Science. This is this red building here. It's an institute where the building itself is about $150 million, and this institute will focus on nanoglass alloys technological application. It has a structure of a Max Planck Institute, only English spoken, only young people that speak up. And so it's a new kind of structure which is set up by the Chinese Academy of Science. I wanted to point that out because that will change the landscape in science very soon. It's not only this institute, they copy the Max Planck Institutes of Germany in very different fields, in artificial intelligence, in chemistry, in nuclear science, and this will be on new terms of material science. With this kind of remarks, which goes into the political side, I would like to close. Thanks for the invitation, and thank you for the attention.